Howdy students, in this video we're going to talk about the enthalpy change for a system. Specifically, we're going to talk about phase changes, so going from solid to liquid, liquid to gas, maybe even jumping from solid to liquid to gas, or gas to liquid to solid. So the first thing we need to understand is this word called enthalpy. It's represented by the letter H, a capital H, and it is defined by the amount of heat in a system at a given temperature. So with Q, we learned that that was heat energy, and we learned that we could calculate the heat energy with the mass, the specific heat, and the delta T, the change in temperature. So what we're going to look at is the change in heat of a system at a given temperature here. So we have two types of system heat changes. We have exothermic reactions and endothermic reactions, or we could say endothermic processes. If it's exothermic, delta H, the enthalpy change, the heat change, is going to be a negative value. Endothermic reactions have a positive delta H, which means that energy is actually absorbed. So we have two diagrams down here on the bottom. For an exothermic reaction, we're going to start with a high energy. The reaction is going to start. We're going to need a little bit of inputted energy. And eventually, we'll be able to start producing products. And what we finish at is a lower energy. So the change in enthalpy, the change in heat, goes from a high number to a low number. So we're actually releasing heat here. And then here it's the opposite for an endothermic reaction. We start at a lower energy. We need a lot more energy to get the reaction started, but then we finish at a higher. So the change in enthalpy, we are actually absorbing heat. So we're not going to talk about it in this video, but we can calculate the enthalpy change of a chemical reaction. So for on this slide, what we want you to understand is if we did have a chemical reaction, where would the energy be placed in the reaction? So here in the first one, we have methane with oxygen in a combustion reaction to produce CO2 and H2O. It's an exothermic reaction, which means energy is released. You'll see a negative value for the energy. And what you'll notice is that the energy there in kilojoules is on the product side. Now, if you have another reaction down here, you have H2O yielding H2 and O2. It's a decomposition. You'll see a positive value for delta H, which means it's endothermic, and energy is absorbed. So when you have a positive value, you'll see your energy on the left side of the reaction as a reactant. And we'll actually have some examples of that in our second video. So as a recap, exothermic energy is a product. Endothermic energy is a reactant. Delta H is also known as heat of reaction. So we're going to focus in this video on the heat change, the delta H, of a change in state. So solid to liquid to gas, or back and forth. So there's a couple of values that we need to have so that we can use them. Specific heat for liquid water is 1 calorie per gram Celsius. And I want you to write this in your notes, but we also have these units in joules, 4.18 joules per gram Celsius. The specific heat of ice, which is a solid, is 0.5 calories per gram Celsius, or I would write this in your notes, 2.1 joules per gram Celsius. And then for steam, which is a gas, 0.5 calories per gram Celsius, or I would add this to your notes as well, 2.0 joules per gram Celsius. So whatever you need your heat units in, either joules or calories, you can use either one of these values here. Okay, a couple other things we need to know as far as some data we can use, a constant value we can use to calculate the heat. We have the heat of fusion, which is the heat required to melt 1 mole of a solid. So I would underline or circle melting. Fusion and melting are the same thing. Molar heat of solidification, heat released as 1 mole of liquid freezes. So here, solidification would indicate freezing. So melting would be solid to a liquid. Solidification would be liquid to a solid. So the heat of fusion for water equals 6.01 kilojoules per mole, or 334 joules per gram, which also equals the heat of solidification. If we are going from a solid to a liquid, we're absorbing energy. So heat of fusion is going to have a positive value. If we're freezing, we're going from a liquid to a solid, which means we have to release heat. So those are going to be negative values. So you'll change the sign depending on which direction you're traveling. The equation we're going to be using there is Q equals M times the heat of fusion or the heat of solidification. So we'll either have a mass or we'll have an amount in moles. The heat of vaporization is the heat required to vaporize 1 mole of a liquid. So here we're going from a liquid to a gas. Heat of condensation is the heat released as 1 mole of gas condenses. So that would be gas to a liquid. The heat of vaporization of water is 40.7 kilojoules per mole, or 20 to 60 joules per gram. The value is the same for condensing or vaporization, but again, if we're vaporizing, it's going to be a positive value. If we're condensing, it's going to be a negative. The equation is the same, but it's going to be mass times vaporization or condensation, and we're going to use these values. So to find the energy released in a phase change, which again is solid to liquid to gas or back and forth, Q is going to equal the number of moles, so N or M if we have mass, times the delta H for vaporization, fusion, condensing, or solidification. So you got 4 different values that you can use there. Temperature is constant during a phase change. We'll see this when we draw out our heating curves in just a moment. So at the end of this video, we're going to look at this heating and cooling curve. It shows the energy changes of matter when energy is added or lost. So I'm going to add a few things to this. This is in your notes. In class, I actually draw this a lot larger and include some things. So if you need more space, pause the video, draw this on the back because I'm going to add a few things. The first thing would be the horizontal portions of the curve. Okay, the horizontal portions represent a phase change, and you'll see that, freezing and melting, condensing and vaporization. So what I'd like you to write is the equation that you use here, which is Q equals M times delta H. Q equals M times delta H. However, there's a change in particle position at these spots, so there's a change in potential energy. So that's the equation we use on the horizontal. Now, on the sloped portions, there's actually a temperature change because on the y-axis, you have temperature. So on the sloped portions, you're going to be using Q equals MC delta T. Q equals MC delta T, and Q equals MC delta T. So we have 5 steps to this diagram: solid, melting to a liquid, and then liquid to a gas, and then we have gas. A couple other values I would add. Right here, I'm going to take my values. The specific heat for ice is 0.5 cals per gram Celsius, or 2.1 joules per gram Celsius. The specific heat of liquid water is 1.00 cal per gram Celsius, or 4.18 joules per gram Celsius. And then the specific heat for steam is 0.5 calories per gram Celsius, or 2.0 joules per gram Celsius. Now, on the other hand, you have values for M delta H. So for the delta H values, for vaporization or condensation, we have 40.7 kilojoules per mole, or 2260 joules per gram, depending on the unit that you need. And then I'm going to go back real quick, catch this value that I missed. Six, so the delta H for freezing, or the delta H for melting, 6.01 kilojoules per mole, or 334 joules per gram. Okay. The next video, we're going to work through some examples using this heating and cooling curve.